Hello, class. So this lecture, we're going to cover magnetism and electromagnetism. Okay, so for the first little bit of the lecture, a little bit of the PowerPoint, it's very theoretical, just to let you know. We're talking about magnetism and how magnetism works. The reason we're talking about magnetism, why it's so important to talk about magnetism, is it is one of the 5 sources of electricity that we talked about previously. Okay. So magnetism is used throughout vehicles. It's used throughout electric motors, through relays, through solenoids, through the ignition system. Any electric motor, like say your window motor, your sunroof motor, your power seat motor, those all use magnetism to work. And then ignition coils and relays, which are switches, and solenoids, which are a different type of switch. Those all use magnetism as well. Okay. As we're going through the PowerPoint, make sure you write down all the highlighted verbiage. Anything that is highlighted and bolded, like this wording right here, as we see on the page. Let me circle this for you. Make sure you write all that down, okay? Because that will be on the quiz of some sort. All right. So first thing first, I think everyone kind of knows this, especially from like basic science back in elementary school. Our magnets that we have. So if we have 2 magnets, they either repel or they attract. So if they repel, they are both facing each other in the same pole, so to say. So if a south pole and a south pole face each other and we try to push them together, they will repel. They don't want to go together. Same thing if we put north and north together. Okay. But if we and think of south and north as positive and negative. Okay. If we flip it around though, we flip one of them around and we try to put south to north or positive to negative, what do? They attract and they try and pull together. Okay. And those are the basics of just basic magnetism that we're talking about for right now. As we move on, this diagram, or sorry, this picture just shows how magnetism would work. So if you want to do this, I think some people may have done this in elementary science classes or even middle school or high school science classes. You put a piece of paper down, you put some metal shavings on top of the piece of paper, and then you put the magnet underneath the piece of paper, and that'll show you how the magnet moves and attracts and moves the metal pieces around. Okay, so again, just write down the verbiage as we see that's highlighted for sure. Okay, so we also find magnetism in ABS wheel speed sensors or any type of sensor that has 2 wires. Now, the sensors that have 2 wires, they produce electricity, and the way they produce it is through magnetism. Within the sensor itself, there's a coil. The coil is basically a piece of wire that's wrapped around a piece of metal. Now that wire, and then there's 2 ends to it. The 2 ends of the wire come out into the sensor, into the wiring of the sensor, and go back to the module. When we have a tone wheel or reluctor, see the wheel that is, or not the wheel, I should say, the one with the teeth. I'll circle them here on the picture and circle here on the drawing. That wheel there is metal also. And when we put the 2 metal pieces really close together, so we have the sensor, which is pointed towards the wheel, and then we have the wheel that's spinning. By doing this, by having these really close together, they don't touch at all. But by having them this close together, what happens is AC electricity is generated. So, okay, so the key is that AC, alternating current, is generated. AC voltage. Okay. And this is using magnetism to create this. And then we can use those signals to be able to communicate or be able to use that information by the control module to determine how fast the vehicle is moving or how fast the engine is moving. So it's used to determine speed is what it is. This is more theoretical, but if we want to know which way the magnetic field is flowing, we can use the left-hand rule or the right-hand rule. Go ahead one slide. So this is the right-hand rule, this picture. I'm gonna go back one. This is the left-hand rule. Okay. Again, just looking at, this is just more for the engineering and for the theoretical portion of it on understanding which way the magnetic field is going to flow. For our purposes, when we're repairing vehicles, working on vehicles, we really don't need to know this. But if you're interested in the theory behind it, this is what the theory is talking about, the left-hand rule, right-hand rule. and how engineers and physicists and people that design these vehicles understand which way the magnetism is flowing in which direction. Okay, just another picture. Again, the PowerPoint is available for you to go through by yourself too, if you like. You can go through it and look at the pictures, in more detail, and if you have more time. Now we have a relay. So we talked about relays previously, but the thing with a relay has a movable arm, also known as a switch. Okay, think of a relay as basically a switch. Why do we use a relay instead of just a switch? The main reason is we have a high amperage circuit. The only time we use a relay is in a very high amperage circuit, such as an AC compressor, a starter motor, a blower motor, the AC fan that blows air onto you when you turn your AC on. So those components, they draw a lot of amps. They use a lot of amperage, which is the amount of electricity. And for that reason, we need relays to be able to help us to turn those items on. Could we wire them directly to battery and use a switch and use a ground and wire it directly to the high amperage motor? Yes, we could, but the size of the wire would be very, very big. So we'd have to use probably a gauge by like somewhere between 4 and 8, somewhere around there. Maybe 10, right? But the thicker the wiring, yeah, it can handle the extra amperage, but the issue is it's going to cost more, a lot more too. And if we do that with, thousands or millions of cars that are built, then we're going to lose a lot of money. The manufacturer is going to lose a lot of money in that instance. So it's actually more cost effective and better designed to use a relay instead. Okay. And this is just a drawing of a relay and how it could be wired. So, take a moment to look at that if you like. Instead of using so there's a relay, which is a electromagnetic switch. It uses magnetism. So we energize the coil. And when we energize the coil, which is the part I just circled here, and we can see the coil has roughly 60 to 100 ohms. Sometimes they have more than that. But the switch, which is the other portion, which I just circled over here, so where it's normally closed or normally open, that is the switch portion. So when we energize the coil, we pull the switch towards the coil, which and then uh, makes contact with the switch. Okay, the contact will be made, and then that'll turn the item on. But what we're controlling is we're controlling electricity to the coil. We're not controlling electricity to the switch, but to the coil. It magnetizes it and pulls the switch closed. That's how the relay works. Now a solenoid, which is this over here that I just circled on the right, this item, this is a movable core. So this acts like a piston that comes out, so to say. And that's another type of switch. So that's kind of like a plunging type of switch. So when we energize the solenoid, the plunger comes out. Okay, it goes in one direction. The solenoids are used on starter motors. They're also used in transmissions as well to shift gears. So we can use the solenoid to be able to push something. The spring is what returns it. That's why there's a spring located on there. You can see the spring there. Okay. So the spring again returns the movable core from the solenoid, but the electricity is what pushes the solenoid out and thus acts like a switch to turn something on or off or move something. And here's a starter motor, picture of a starter motor. The solenoid is right here on the top. It's the smaller cylinder. And that solenoid is going to kick out the gear on a starter motor to be able to turn the flywheel to be able to start the car. Okay. Now we'll get into just a little explanation about how electricity is created through magnetism. So we use electromagnetic induction. What this basically means is we have a stationary coil or piece of metal that's wrapped around with wire wrapped around it. And then we have another piece of metal that has wire wrapped around it, possibly can or cannot. Or we could use a permanent magnet and we put them really close together, but they don't touch. Okay, that's the thing. They don't touch, but they're really close together. But we spin one of them. As soon as we spin one of them and we hold one stationary, that's when we start to create magnetism. Okay, if we want to create more magnetism, sorry, that's when we create electricity and magnetism, I should say. Magnetism is created, but also electricity is created as well. Now, in order for us to create more voltage, so as we want to get more electricity out of it, we increase the speed. So your alternator will produce so much voltage at idle, but if we want to increase it, we just drive it on the freeway and the voltage will increase for the alternator. Okay. And at the end, if we want to increase the strength of the magnetic field, which will in turn create an additional voltage and amperage, we can increase the number of windings or increase the magnetic field itself. So get bigger magnets or bigger windings and bigger coils. Okay. And then this is just a little definition here for you guys. Just make sure you write this down. Again, magnetic field strength is measured in ampere turns. So it's more like a definition. The measurement we use, how do we measure magnetic fields, is the word ampere turns. Now, ignition coils. Ignition coils are a little complex. These are covered more in a different class, which is engine performance. But for here, the basic definition of a coil, or what a coil is a step-up transformer. Okay, step-up transformer. So a transformer, what a transformer does is it changes the voltage from low to high or from high to low. Okay, so in our instance, we're changing it from low to high. So low voltage in the battery, we always have 12 volts in our normal automotive batteries, right? With the engine on idling, it's roughly 13 and a half to 15. But we have 12 volts in our battery. But our ignition coils, if anyone knows anything about ignition coils, I don't expect anyone to in this class, but ignition coils require a lot more voltage than 12. They require somewhere in the thousands. Okay, I would say 10,000 to maybe as high as 60,000, maybe even higher, depending if they're towing something or if you're going up a hill or you're racing. You know, the higher the load on the engine, the more voltage it'll need. So we're talking thousands of volts. How do we get 12 volts to turn into 10,000 volts? We do it through magnetic induction or mutual induction. And it's through a step-up transformer, which is also known as an ignition coil. So the way it works is we have an ignition coil, we have a primary side, and we have a secondary side. Now, the different sides have uh, different windings. Okay, so the primary side is the 12-volt side. So this is 12 volt here. And then the other side, which is the secondary side, that's the high voltage side. So I'm going to put high voltage. Okay. And these, again, these sides, you notice they're not touching. So, and they're not supposed to touch. What we do is we energize the 12-volt side, because that's the side we can control with the ECM. So the engine control module will energize it. It'll bring the voltage up. It creates a magnetic field because there's a coil around here, around this piece of metal on the primary side. There's also a coil on the other side. You know, you can notice that the windings are slightly different. But there's also a coil on the other side. By having these magnetic fields, they're going to be really close together. We're creating a magnetic field on the left side, which is the primary side, which induces a magnetic field on the right side, which is the secondary side. Now, both of them are magnetized when the circuit is on, the switch is on. As soon as we collapse or turn off the switch, though, on the primary side, which is the 12-volt side, the voltage in the coil simply goes back to ground. That's all it does. Just goes back to ground and no problem. Goes back to the battery. Okay. But we have a magnetic field on the primary side, which is on the high voltage side. That side is not connected to the battery. So it has to go somewhere because we just removed its source of power, its source of magnetism. Now, in order for this to work, what this magnetism and electricity is going to do, it's going to go into the spark plug. It has to find a ground. It has to get out of here. It has to get out of the coil. So it's going to go through the spark plug. It's going to jump the gap of the spark plug and go to ground, which is the engine block. The engine block is ground. But by doing that, it creates a spark. And if we time it correctly, that's what ignition timing is. We're going to time it when the engine is at a certain degree, a certain point where we want it. We inject fuel and air at the same time, and then it ignites through that spark. Okay, so this is the spark system of the engine. Okay, again, I don't expect everyone to remember all that. You know, as we talk about it more, as you hear it more from different people, different classes, different instructors. Maybe it'll stick at some point. Okay. But again, this is mainly covered in a different class, but I at least want to get to the concept of mutual induction or electromagnetic induction. Again, here's just a different type of coil or different coils that are designed. But again, remember the coils are not connected. The primary side and the secondary side are not connected. They can be connected, like the picture at the top. That is an option for them to be connected. Okay. Um, and if so, then again, when there is that collapse, we could just go straight back to ground. But the main collapse of the magnetic field on the secondary side is always going to go through the spark plug. Okay, that's what we need that spark for, to be able to spark, jump the gap, and spark the spark plug. Okay, and ignite the air fuel mixture. Some of the I'm not gonna go over this so much, but the some antennas, again, we're looking at a ground wire here, ground strap, a flexible ground strap, and just make sure you read everything that's here. But the ground straps, definitely help with interference, especially when it comes to radio and audio equipment. And again, that's what we're talking about here too. So in order to reduce electromagnetic interference, which we would hear as like noise, static in the speakers. There's different ways to do it, but electromagnetism can help with it. We add resistors, we add capacitors, or we add coils into the electrical system, and that can help reduce those. Okay, again, make sure you pause and read as we're going through. Last small section is going to cover capacitors. Capacitors are very, very easy to understand. Capacitors basically store electricity. They store it not like a battery does, but they store it in a sense like a temporary storage facility for electricity, and it can be used really fast as much as it wants. If we drain a battery, the battery will not be any good anymore. We can't drain a battery down to zero. That's not good for batteries. But a capacitor, we can charge a capacitor. It can go up to 100%, and then we can use it and drain the capacitor all the way down to 0% and then charge it back up. And it'll work, no problem. It keeps doing that over and over again. The thing with capacitors, though, they're not designed to store electricity for a long period of time. For instance, your battery in your car, you can go and you park your car and you can come back in a month. As long as the battery's good, it'll be there. It'll start, it'll be fine. Um, it might be a little bit low on charge, but it should work fine. If we do that to capacitor, we charge a capacitor, we come back in a month, it'll be gone. The electricity won't be there anymore. Okay. So those are the differences. But we only use the capacitors in a instance where we need a lot of electricity, a lot of power right away, and only for a very short period of time. For instance, they're used in audio systems a lot. Okay. Make sure you go through this slide and look through this, or make sure you read this. Okay. I'm not going to go through this one because I want to get to, again, same thing with here. Make sure you read this and go through this as we go through the next one. These are just the symbols. Sorry, I was trying to get to there we go. I was trying to get to this one. I'm going to come back. So one of the main purposes of capacitors, at least that may be common to most people that many have seen, is in audio systems. So when we have amplifiers and high power audio systems, we need additional power. You can add an additional battery, which would help, but you can also put additional capacitors too. The capacitors are used when the audio system needs it, which is usually when there's a song or sound that is very, very loud or requires a lot of power, like when there's a song with a lot of bass, then the capacitors will be used when the bass is very loud. Okay. And then it'll charge back up and then be used again, then charge back up and used again over and over again. So that's really where the voltage supply comes into play. Okay. We can let me go back. I'm sorry, I was gonna go back to this slide here. This slide here shows the symbols of a capacitor. Okay, so this is the main one that we use, that we usually see, the upper left one. This one we see as well. Okay, not as common, but they are there. And these are mainly fixed capacitors. Okay, so they don't change. There are some things as variable capacitors, but they're not used very often in cars. Okay, at least for our purposes. The other thing is too, we do not usually change capacitors. Capacitors are usually within an electronic component. You can add a capacitor into your audio system, but that would be something aftermarket. That's not something that would be come from the factory. Okay, so just make sure you write down up here what it says at the very top. Um, capacitors block direct current, but they let alternating current pass through. Okay, and we've already went over this slide. Again, make sure you write down everything that is highlighted in yellow. The uses for capacitors. Again, we can store electricity, we can reduce noise with them, they can act as timers, and they are used in these components here, microphones, radios, and speakers. Okay. Now, if we wire a capacitor in parallel, this is kind of important, we increase the capacity. So it gets bigger, like we're making a bigger, better capacitor. We have to wire it in parallel though. And as you can see here, we have a parallel circuit because we have three sources of electricity or three sources, three power sources or power paths and three ground paths as well. Okay, for the capacitors. So if we wire everything in parallel, we increase the capacity. Okay. And the last slide here, the last usage of a capacitor besides a resistor is to reduce voltage spikes. So in computers, we could have voltage spikes. We don't want to have voltage spikes in computers, and we could add a capacitor. So it's that there's multiple uses for capacitors, for resistors, for coils, stuff like that. So in this diagram here, this is just showing you an example. But the one here with the speakers, we have a capacitor, we have a coil, and we have a resistor. We're adding all these things in to help reduce noise, to make sure that there's no static in the speakers and there's no feedback. So these things can be added throughout. Okay. Let's just show an example of how they can be added and how they can be wired into a speaker circuit. Then the last picture that I just want to discuss briefly is up here where these capacitors are wired in series, as you can see. Okay. And series decreases the capacitance. So it actually does the opposite job. You would not want to wire them in series. That would not make any sense, because one capacitor would feed the other one, then would feed the other one, then would feed what you want it to feed. But that would act just like one capacitor. So what's the point? So yeah, we do not want to wire them in series. They decrease capacitance. If we want to wire them properly, we would wire capacitors in parallel. Okay. So again, if you have any questions, always feel free to reach out to me. Hopefully you've enjoyed this section of the class. Again, reach out to me whenever you have questions. Okay. Thanks a lot.